Right now, in the tips of your fingers, in the soft tissue of your eyelids, in the still air just above your skin, something is happening that no one can see and no one can stop. Electrons are shifting position around the atoms that make up your body. Photons of infrared light are leaving your skin and drifting into the room, carrying away a small, constant trickle of warmth. Atoms in the cotton or linen touching your shoulder are exchanging tiny packets of vibration with the atoms in your skin, and this exchange never fully stops, not even when you are lying perfectly still, not even when you are asleep. It has been happening since before you were born, and it will keep happening after you drift off tonight, quietly, without asking your permission or requiring your attention. You have never once had to instruct your body to do this. It simply does it, the way a candle simply burns, the way a tide simply rises, because this is what matter does when it exists at all. If you could shrink yourself down, smaller than a dust mote settling on the blanket beside you, smaller than the weave of the fabric itself, you would find that this warmth leaving your skin is not a smooth outward breath, the way heat seems to drift off a teacup in lazy curling wisps. It is more like a fine, continuous rain of individual droplets, each one carrying away a specific, non-negotiable amount of energy, no more and no less. You cannot see this happening, and you were never meant to. It happens at a scale so far beneath ordinary perception that human beings spent the vast majority of their history on this planet without ever suspecting it was there. And yet it was always there, underneath everything, the quiet architecture holding up the world you can touch. This constant, invisible activity is where our story begins tonight, because it turns out that everything solid, everything warm, everything glowing gently in the dark, is built from a kind of behavior that nature seems to insist on, not a behavior we invented, not a rule we imposed. A behavior we discovered, almost by accident, a little over a century ago, when a small group of physicists sat down to solve what looked like a fairly ordinary problem, and found themselves instead standing at the edge of something enormous. The word for what they found is quantum. It sounds technical, maybe even intimidating, but the idea underneath it is simple enough to hold in your mind the way you might hold a single warm stone. Quantum comes from the Latin word quantus, which simply means how much. That is really all it is asking, how much. It is a word about counting, about there being a smallest unit of something, a smallest step you cannot divide any further. Think of coins in your pocket. You can have 1 penny or 2 pennies or 17 pennies, but you cannot have 1.5 pennies. The penny is, in that sense, a kind of quantum of money. It comes in a smallest piece, and every larger amount is simply that smallest piece added to itself, again and again. You could also picture the stairs leading up to a front porch, worn smooth by decades of footsteps. You can stand on the first step, or the second, or the fifth, but there is no place to stand between them. The space between 2 stairs is a place your feet simply cannot occupy, no matter how gently you try. For a very long time, nobody thought that light or energy or the motion of tiny particles worked this way. Scientists in the 1800s, watching heat and light behave, generally assumed that energy was more like water than like coins. You could have any amount you wanted, any amount at all, flowing smoothly from a little to a lot, the way you can pour a thimbleful of water or a bucketful, with nothing in between forbidden, smooth, continuous, endlessly divisible. That assumption fit almost everything they saw. It fit falling apples and orbiting planets and the graceful arc of a thrown ball. It fit the tides and the seasons and the slow cooling of a cup of tea left on a windowsill. The mathematics of the era, built patiently over 2 centuries by minds like Newton's and later refined by generations of careful successors, described a universe of smooth curves, unbroken lines, and gradual change. There seemed to be no reason to expect anything else. But there was one stubborn puzzle that refused to fit. Physicists were trying to understand something called black-body radiation, which is really just a fancy way of describing the ordinary glow that any warm object gives off. Heat a piece of iron in a forge, and it will begin to glow, first a dull red, then orange, then a white so bright it hurts to look at. Blacksmiths had known this by instinct for thousands of years, reading the temperature of their metal from its color alone, long before anyone thought to ask why the color changed the way it did. The color and brightness of that glow depend only on temperature, not on what the iron is made of, and by the late 1800s, physicists had worked out very careful mathematical descriptions of light and heat that should have explained this glow perfectly. Instead, when they used those descriptions to calculate how much energy a hot object should radiate at very short wavelengths, the equations gave an answer of infinity. Not a large number, not an inconvenient number, infinity, an answer that could not possibly be true, since it would mean that a warm poker sitting in a fireplace should be blasting out infinite ultraviolet light and instantly destroying anyone nearby, the iron in the room, the very air surrounding it. Physicists at the time actually had a nickname for this embarrassing failure. They called it the ultraviolet catastrophe, and it sat there, unresolved, for years, a crack running through an otherwise confident and successful branch of science. In the year 1900, in Berlin, a German physicist named Max Planck decided to try something that even he did not fully believe in at first. He was a careful, rather conservative man, deeply devoted to the elegance of classical physics, not someone inclined toward wild speculation, and by his own later account, he approached this idea reluctantly as what he called an act of desperation. He had already spent years trying to force the old, smooth mathematics to behave, adjusting formulas, testing variations, and none of it worked. What Planck proposed instead was that maybe energy, at least in this situation, did not flow smoothly like water after all. Maybe it came in discrete little packets, chunks of a fixed minimum size, and objects could only absorb or release energy in whole multiples of that chunk. Not 1.5 chunks, not 1/3 of a chunk, whole chunks only, exactly the way you can only spend whole pennies, exactly the way your feet can only rest on a whole stair. When Planck did the math this way, treating energy as if it came bundled into these small, indivisible portions, the terrifying infinity in his equations vanished, almost as if a fog had lifted from a familiar landscape. The numbers settled down into a curve that matched, almost perfectly, what experimenters had actually measured when they pointed their instruments at warm, glowing objects, tracing the exact rise and fall of brightness across every wavelength, exactly as the glowing iron or the surface of a distant star would show it. He called the size of that smallest packet a quantum of action and gave it a specific numerical value, a number so small that in everyday units it is written with more than 30 zeros after the decimal point before you reach the first meaningful digit. To picture a number that small is almost beside the point. What matters is that it is not zero. It is small enough to be completely invisible in the ordinary events of daily life, small enough that a falling apple or a swinging pendulum shows no trace of these steps at all, and yet large enough, when multiplied across the almost uncountable number of atoms in a heated object, to reshape the entire behavior of light and heat. Physicists later named that number Planck's constant, and it remains, to this day, one of the fundamental numbers that describes the shape of the universe. Sitting quietly alongside the speed of light and the strength of gravity, as one of the handful of constants nature seems to have fixed once and never altered since. Planck himself did not fully embrace the strangeness of what he had found. For years, he seems to have hoped that this graininess of energy was some kind of mathematical convenience, a useful trick rather than a true description of nature, the way you might round numbers in a calculation without believing the world itself is rounded off at the edges. He wanted, quietly, for the old smooth picture of the universe to still be correct underneath it all, for his packets to turn out to be nothing more than a clever shortcut. It took another physicist, working in a patent office in Switzerland 5 years later, examining patent applications by day and turning these puzzles over in his mind by night, to argue that these energy packets were not just a convenient bookkeeping device, but something real. That physicist was a young man named Albert Einstein, and in 1905, the same remarkable year in which he also published his theory of special relativity, a year so productive that historians now simply call it his miracle year, he proposed that light itself, not just the energy exchanged by glowing objects, might actually travel through space in these discrete packets. He used this idea to explain another puzzle, one involving light striking a metal surface and knocking electrons loose from it, a phenomenon that had been observed in laboratories but never properly explained, since the old wave picture of light predicted results that simply did not match what experimenters saw. Einstein's packets of light would later be given a name of their own. We now call them photons, the very same photons drifting quietly off your skin right now, carrying their small, fixed portions of warmth out into the dark room around you. So here is where we find ourselves, gently, at the beginning of this journey. The word quantum does not name some exotic, distant phenomenon locked away in a laboratory you will never visit. It names a simple mathematical fact that nature apparently insists upon. Certain things in this universe, certain kinds of energy, certain properties of certain particles, do not come in smooth, continuous amounts the way water fills a glass. They come in steps, in indivisible units, in countable pieces, the way coins fill a jar, the way footsteps fill a staircase. This is a strange thing for nature to insist on, strange enough that it took brilliant, careful people years to accept it themselves, Planck most of all, and strange enough that it would go on to reshape almost everything physicists thought they understood about light, about matter, about energy, and eventually about the very atoms sitting quietly in your body right now, glowing faintly in the dark, exchanging their small packets of warmth with the room around you, following rules that no one designed and everyone had to slowly, patiently learn to see. And it is exactly there, with those quiet atoms and their invisible steps, that our next question begins to take shape, because once you accept that energy comes in these small, countable packets, you have to ask what that means for the tiniest pieces of matter itself, the electrons and atoms that make up everything you can touch. Let's go back a little further, though, before Einstein, before 1905, to a quieter and much less famous problem that had been bothering physicists in the closing years of the 1800s. It did not sound like the kind of puzzle that could upend physics. It was, on its surface, about something as ordinary as heat. Picture an oven, or better, picture a kiln, the kind a potter might use, sealed on all sides except for one small hole cut into it. Heat that kiln up, and the hole will begin to glow. At lower temperatures, the glow is a dull, deep red, like the coals at the bottom of a dying fire. Push the temperature higher, and the glow shifts, brightening toward orange, then yellow, then, if you could somehow keep going without melting the kiln itself, toward a blue-white brilliance. Physicists called the light coming from that small hole blackbody radiation, and they studied it not because they cared about pottery, but because that little glowing hole was, in a strange way, one of the purest and simplest light sources in the universe. It did not depend on what the kiln was made of. It depended only on its temperature. That simplicity made it a perfect testing ground for theory, because if you could not explain something this clean, this stripped down, you could not really claim to understand light and heat at all. And for a while, it seemed as though physicists could explain it, at least approximately. Using the established laws of thermodynamics and electromagnetism, laws that had been tested and trusted for decades, they built a formula to predict exactly how much of each color, each wavelength, would come pouring out of that hole at a given temperature. At longer wavelengths, out toward the red and the infrared, this formula matched what experimenters actually measured almost perfectly. It was a genuine triumph, the kind of quiet mathematical victory that a physics department in Berlin or Cambridge might toast with tea and mild self-satisfaction. But something went wrong as the wavelengths grew shorter. As the formula was pushed toward the blue end of the spectrum and then past it into the ultraviolet light that human eyes cannot see, it stopped agreeing with experiment and instead began predicting something absurd. It suggested that the kiln should be pouring out not just a little extra light at those short wavelengths, but an infinite amount of energy, an endless torrent of ultraviolet radiation and beyond, radiation that would, if the formula were correct, blind and cook anyone standing anywhere near a warm object at all. Obviously, this does not happen. You are not being bathed in lethal ultraviolet light by the warmth of your own bedroom right now, and neither was anyone in 1899. The formula, trusted and well-built as it was, broke completely at short wavelengths, predicting a runaway of energy that the real universe simply refused to produce. Years later, a physicist named Paul Ehrenfest gave this failure a memorable name. He called it the ultraviolet catastrophe, and the name stuck, the way a good name for a problem often does, because it captured both where the trouble occurred and how seriously physicists eventually came to regard it. It fell to a rather cautious, formal, and by most accounts quite conservative physicist in Berlin to find a way out. His name was Max Planck. He was not a young rebel eager to tear down the physics of his elders. He was, if anything, the opposite, a man deeply devoted to the classical thermodynamics he had spent his career mastering, someone who by his own later description had little interest in overturning established laws and every interest in defending them. In the closing weeks of the year 1900, working late, revisiting the mathematics of blackbody radiation again and again, Planck found that he could make a formula fit the experimental data perfectly, across every wavelength, short and long alike, but only if he introduced one deeply strange assumption. He had to suppose that the tiny vibrating charges inside the walls of that glowing kiln, the oscillators, as physicists called them, could not exchange energy with the light around them in just any amount they liked. They could only give up or absorb energy in specific, fixed portions, portions whose size depended on the frequency of the vibration and on a new constant of nature, a very small number that Planck introduced into his equations almost as a mathematical convenience. That number is still called Planck's constant today, and it is one of the most fundamental figures in all of physics. But at the time, it was simply the number that made an otherwise broken formula work. Planck himself described what he had done in a phrase that historians of science still quote, calling it an act of desperation. He did not reach for these discrete packets of energy because some new experiment revealed them directly, or because a beautiful new theory demanded them. He reached for them because nothing else fit the data, and after years of trying every other reasonable approach, this strange assumption was the only door left open. It is worth sitting with that for a moment, in the quiet of whatever room you are lying in now. One of the strangest ideas in the history of science was not proposed with excitement or triumph. It was proposed reluctantly, almost apologetically, by a careful man who suspected, or perhaps simply hoped, that it might eventually be explained away by some deeper, more familiar piece of classical physics that he simply had not found yet. And this is where the story asks for some real historical care, because it is easy, looking back from over a century later, to imagine Planck as the founder of quantum theory in the bold sense we now use that word, a man who saw that light itself comes in particles and announced it to the world. He did not do this. Planck's own quiet position, the one he held for years afterward, was much narrower than that. He believed that the energy exchanged between matter and radiation, the giving and receiving of energy between the oscillators in the kiln wall and the light bouncing around inside it, had to happen in these discrete steps. But he did not believe, at least not at first, that light traveling through empty space was itself made of discrete little bundles. In his view, the packets were a property of the exchange, a kind of toll paid at the border between matter and light, not a property of light itself, once it was out there traveling freely through the room. It was a subtle distinction, but Planck held to it carefully, the way a careful person holds to any claim they are not yet fully certain of, several years after his own equation began quietly reshaping physics around him. It would take Einstein's paper of 1905, the one proposing that light itself moves through space as individual packets, to push the idea further than Planck himself was initially willing to go. And even then, many physicists, Planck included for a time, remained hesitant, uneasy, waiting for confirmation, the way anyone might wait before fully trusting a strange new idea, even one they had helped bring into the world themselves. So, the quantum story does not begin with a flash of certainty. It begins with a stubborn mismatch between theory and experiment, a formula that broke in the ultraviolet, and a cautious man who found a fix he did not fully believe in yet. And from that small, reluctant beginning, the question would only grow larger, because if energy really does move in these discrete, countable steps, the next place to look, quite naturally, is inside the atom itself, where electrons circle and settle, and somehow, mysteriously, never seem to fall. Before we get to the atom and its strangely stable electrons, there is a detour worth taking, a quieter experiment that had been puzzling physicists for years, one that did not seem, at first glance, to have anything to do with Planck's kiln or his ultraviolet catastrophe at all. It involved metal plates and light, and a small, persistent oddity that refused to make sense under the old wave theory, no matter how patiently anyone worked through the equations. Here is the setup, and you can picture it simply enough. Take a clean piece of metal, something like zinc, and shine light on it. If the light is energetic enough, something curious happens. Electrons come loose from the surface of the metal and fly off into the surrounding space. This is called the photoelectric effect, and by the 1890s it was a well-known phenomenon, something several physicists had already observed and measured, including a German scientist named Philipp Lenard, who spent years studying exactly how these freed electrons behaved once they left the metal. Under the wave theory of light, the theory that had worked so beautifully for so long, the theory that explained interference patterns and diffraction and nearly everything else light seemed to do, there was an obvious prediction for what should happen here. Light was understood as a wave a smooth, continuous ripple of energy spreading outward, the way ripples spread across a pond after a stone breaks the surface. And if light is a wave, then a brighter light, a more intense one, should simply be a bigger wave, carrying more energy overall, spread across the same rolling motion. Turn up the brightness, and you turn up the total energy arriving at the metal. It seemed reasonable, almost obvious, that this extra energy should show up in the electrons that came loose. That brighter light should knock electrons out with more force, sending them flying off faster and harder, the way a bigger wave hitting a shoreline moves more sand than a smaller one. But that is not what the experiments showed. Turning up the brightness of the light did not make the individual electrons fly off any faster. It made more of them come loose, a larger quantity, but each individual electron, once freed, carried roughly the same amount of energy as before, the same speed, the same kick. Brightness, it turned out, controlled quantity, not intensity of the individual event, and that alone was strange enough to sit with for a while, a small crack in an otherwise sturdy wall. The stranger part came next, when physicists started changing not the brightness, but the color of the light, and here, the wave theory ran into real trouble. Color, in the wave picture, corresponds to wavelength, to how long or short the ripples are, how closely packed the peaks and troughs sit against each other as the wave travels. Red light has longer, more lazy waves. Blue and violet light have shorter, tighter ones. And under the wave theory, wavelength should not have mattered very much to whether electrons came loose at all, since intensity, the total energy delivered, was supposedly the thing that governed how forcefully electrons got knocked free. A dim blue light and a bright red light, if you adjusted the intensities carefully, ought to be roughly interchangeable in their effects, each one delivering energy steadily, wave upon wave, patiently accumulating until an electron absorbed enough to break loose from the metal's grip. But that is not what happened either. Shine red light on certain metals, and no matter how bright you make it, no matter how long you leave it shining, no electrons come loose at all. None. You could sit there all through a long evening with a red light blazing at full intensity, and the metal would simply sit there, unmoved, its electrons undisturbed, yet switch to a dim violet light, one so faint you could barely call it bright at all, and electrons would come loose almost instantly, the moment the light touched the surface. This did not fit the wave picture in any comfortable way. If light were simply a wave carrying energy in a smooth, continuous flow, then any color, given enough time and enough brightness, should eventually deliver enough energy to shake an electron free, the way even a small wave, given enough repetitions, will eventually move a pebble on a beach. But that was not what nature was doing. There seemed to be some threshold tied specifically to color, to something about the light itself, beyond just how much of it there was. This is where Einstein enters the story, in that same remarkable year, 1905, when he was still working at the patent office in Bern, examining other people's inventions by day and turning over the deepest puzzles in physics by evening and on weekends. He took Planck's reluctant idea, the notion that energy exchanges happen in discrete steps, and he pushed it somewhere Planck himself had not been willing to go. Einstein proposed that light itself, not just the exchange of energy between light and matter, but light as it exists and travels through space, comes in discrete packets. Each packet carries a fixed amount of energy, and that amount depends only on the color of the light, on its frequency, how rapidly the wave oscillates. Blue and violet light, with their higher frequencies, come in packets carrying more energy each. Red light, with its lower frequency, comes in packets carrying less. These packets are what we now call photons, though that particular word would not be coined until 1926, more than 2 decades later, by a chemist named Gilbert Lewis. Einstein himself, in his own 1905 paper, simply called them quanta of light, or sometimes light quanta, careful, measured language for an idea that was, at the time, almost audacious in what it implied. With this picture, the photoelectric effect suddenly made sense, cleanly and completely. An electron sitting in a metal is held there, bound to the material, the way a swimmer floating in still water is held down by the water's surface tension, needing a certain minimum push to break free and leap into the air above. When a photon strikes the metal, it does not spread its energy out gradually across the surface the way a wave would. It delivers its energy all at once, in a single transaction, to a single electron, rather like one solid coin dropped directly into one hand, rather than a fine mist of change scattered thinly over a whole crowd. If that one packet carries enough energy, more than the minimum needed to free the electron pops loose immediately, carrying away whatever energy is left over as its own speed, its own kinetic motion. If the packet does not carry enough energy, if it is a red photon rather than a blue or violet one, then nothing happens, no matter how many billions of those insufficient photons arrive one after another. A weak coin is still a weak coin, no matter how many of them you stack up, because in this picture, they aren't stacking. Each one is a separate, individual event, given entirely to one electron, and never shared, never pooled together the way a spreading wave might pool its energy across a wide surface over time. And this also explains, quite naturally, why brightness and color turned out to be doing such different jobs in these experiments. Brightness, in the photon picture, is simply a matter of how many of these packets are arriving each moment, how dense the rain of photons is falling onto the metal surface. More brightness means more photons, and so more individual electrons knocked loose, one photon to one electron, a straightforward accounting. But color determines something else entirely, the energy carried by each individual packet, the strength of each individual coin. A dim violet light might deliver relatively few photons overall, but each one carries enough energy on its own to free an electron the instant it arrives. A bright red light might deliver an overwhelming number of photons, more than you could easily count, but if each individual one falls below the threshold needed, none of them, no matter how many, will ever manage to do the job. So light, it seemed, was behaving like a hail of small, discrete bullets when it struck that metal surface, each one arriving whole, each one delivering its energy in a single, indivisible parcel. And yet, only a few decades earlier, physicists had every reason to believe light was nothing like a bullet at all. It was a wave, and the evidence for that had seemed just as solid, just as undeniable. To understand how both of these things could be true, it helps to go back further still, back to a doctor and physicist named Thomas Young, working in London in the early 1800s, long before anyone had heard the word photon. Young wanted to settle a question that had been debated since the time of Newton, who had argued that light was made of tiny particles, little corpuscles shot out from a source in straight lines. Young suspected otherwise. He believed light was a wave, something more like a ripple spreading across the surface of a pond, and he devised a wonderfully simple way to test the idea. He took a beam of light and passed it through a screen with 2 narrow, closely spaced slits cut into it, then let the light fall onto a second screen, placed some distance behind. If light were made of particles traveling in straight lines, you would expect to see 2 bright bands on that far screen, one behind each slit, with darkness everywhere else, the simple shadow of two open doorways. But that is not what Young saw. Instead, he saw a whole series of bright and dark bands, alternating stripes spreading across the screen, growing fainter toward the edges. This pattern is called an interference pattern, and it is the unmistakable signature of a wave. To picture why, imagine two pebbles dropped into still water at almost the same moment, close together. Each pebble sends out its own circle of ripples, spreading outward, and where those two sets of ripples cross each other, something interesting happens. In some places, the crest of one ripple meets the crest of the other, and the two combine, adding together into a taller, more pronounced wave. This is called constructive interference. In other places, the crest of one ripple meets the trough of the other, the highest point of one canceling against the lowest point of another, and the water there stays flat and calm, as though nothing had happened at all. This is destructive interference. If you could freeze that pond and look down at it from above, you would see a pattern of ripples and calm patches, a kind of woven texture, and that texture is exactly the fingerprint of two overlapping waves. When Young sent light through his two slits, each slit acted like one of those pebbles, sending out its own spreading wave of light, and where the two waves overlapped on the far screen, they interfered with each other, bright where the light waves reinforced one another, dark where they canceled out. There was no other way, at the time, to explain those alternating stripes. Particles traveling in straight lines simply could not produce them. Waves could. So there the matter rested for a long while, light as a wave, thoroughly demonstrated, until Einstein came along with his explanation of the photoelectric effect and showed that light also behaved as though it arrived in discrete packets, in photons, each one striking a single electron the way one coin lands in one hand. Both of these things were shown experimentally. Both of them held up, and that left physicists in the middle of the 20th century facing a genuinely strange situation, because a wave and a particle are, by any ordinary definition, opposites. A wave is spread out, extended, present everywhere within its ripple all at once. A particle is a single, localized thing, here and not there, a single small object moving along a single path. Light seemed to be doing both. Then came an experiment that made this stranger still, stranger than anyone comfortable with tidy explanations might have hoped. Physicists began repeating Young's double-slit setup, but this time with electrons instead of light, and eventually with individual electrons sent through the apparatus one at a time, spaced out so that only a single electron passed through the slits every few seconds, with plenty of time between each one for it to strike the detector screen and register a single small mark before the next electron was released. If electrons truly were simple particles, tiny, hard little balls of matter, you would expect each one, over enough time, to build up two clusters of marks directly behind the two slits, the same simple shadow pattern you would get from tossing sand through two holes in a fence. But that is not what happens. Instead, mark by mark, dot by dot, patiently over hours, the electrons build up the very same striped interference pattern that light produced in Young's original experiment, one electron at a time, arriving alone, with no other electron anywhere nearby to interfere with, somehow still produces the signature of a wave crossing itself and interfering. This is worth sitting with for a moment, because it is easy to let the strangeness slide past too quickly. Each electron is a single, indivisible unit. It cannot literally be that one part of it interferes with another part of itself the way two separate pebbles' ripples interfere in a pond, at least not in any straightforward, everyday sense. And yet each individual electron, all on its own, seems to carry within it some possibility connected to both slits at once, some ghost of a wave that passes through both openings and interferes with itself, before collapsing down into a single, sharp point of light on the detector screen. Over many repetitions, thousands upon thousands of these single points, this self-interference builds up into the same striped pattern, bright bands and dark bands, that two overlapping waves would produce. Naturally, physicists wanted to know which slit each electron actually went through. It seems like a fair question, almost an obvious one to ask. So they set up detectors, one at each slit, small instruments capable of registering, in some physical way, whether a given electron passed through the left opening or the right one. And the moment they did this, the moment they had a working setup that could actually tell them which path each electron took, the interference pattern vanished. The stripes disappeared entirely, replaced by that same simple, boring shadow pattern you would expect from ordinary particles. Two clumps behind two slits, nothing more. It is tempting, when hearing this for the first time, to reach for the idea that consciousness itself is doing something magical here, that the electron somehow senses a human mind watching and changes its behavior out of some kind of shyness. But that is not what the evidence supports, and it is worth setting that idea aside gently, the way you might set aside a comfortable but mistaken assumption. What actually breaks the interference is not awareness in any mental sense, not a person's attention or knowledge. It is the physical act of measurement itself, the fact that determining which slit an electron passed through requires some physical interaction with it, some exchange of energy or momentum between the electron and the detecting instrument, and that interaction disturbs the very delicate wave behavior that made the interference possible in the first place. You could remove every human observer entirely, replace their eyes with a simple mechanical recorder that no one ever even looks at afterward, and the interference pattern would still disappear, so long as the recorder genuinely interacts with the electron in a way that pins down its path. It is not about knowing. It is about the physical footprint that any which path measurement necessarily leaves behind. And what that physical footprint actually consists of, what is truly happening at the level of the electron itself when this disturbance occurs, turns out to be a question that takes us even further into how strange, and how carefully described, the quantum world really is. So let's slow down and ask what physicists actually mean when they describe an electron as existing in a superposition, because the word itself tends to conjure up the wrong picture. It is not that the electron is secretly in two places, the way a coin might be hidden under one of two cups while you simply don't know which. That kind of ignorance, the ordinary kind, could in principle be resolved just by peeking, without disturbing anything. What quantum mechanics describes is stranger than hidden information. The electron is described by something called a wave function, a mathematical object that assigns to every possible outcome a number called a probability amplitude. And these amplitudes are not ordinary probabilities. They can be negative. They can even involve what mathematicians call imaginary numbers, numbers that live on a different axis than the counting numbers we use for apples or coins. This might sound like a technical detail meant only for those with equations in front of them, but it turns out to be the very heart of why the quantum world behaves the way it does, so it is worth sitting with for a moment, unhurried. Think of the two slits from before, that softly lit screen, those two narrow openings letting light or electrons through. In the everyday world, if you wanted to know the chance that a thrown dart lands in some region of a target, you would just add up the separate chances from each possible path it could have taken to get there. Straightforward addition, one possibility plus another, and the whole is simply the sum of its parts. But probability amplitudes do not add the way probabilities do. When an electron can reach a certain point on the screen, either by passing through the left slit or the right slit, The amplitude for arriving there is the sum of the amplitude for the left path and the amplitude for the right path. And only after that addition do you square the result, in a particular mathematical sense, to get an actual probability, an actual likelihood you could compare to experiment. This ordering, add first, then square, is where all the magic hides. Because when you add two numbers that can be negative, or that live on that different axis mathematicians use, wonderful things can happen. Two contributions can reinforce each other, making a place on the screen more likely than either path alone would suggest. Or two contributions can nearly cancel, making a place less likely, even impossible, even though either path taken alone would have led an electron right there without any trouble at all. This is the actual mechanism behind those interference stripes, the bright and dark bands we spoke about a moment ago. It is not that electrons are colliding with each other somewhere in the apparatus, jostling for space the way people might in a crowded doorway. Each electron, remember, seems to interfere with itself, arriving one at a time, and yet still building up that same striped pattern over many arrivals. What the mathematics tells us is that the amplitude for the electron going through the left slit and the amplitude for it going through the right slit both exist together as parts of one single wave function, right up until the moment the electron actually lands and a measurement is made. At certain spots on the screen, these two amplitudes add together constructively, doubling and more than doubling the resulting probability, painting a bright stripe. At other spots, they cancel, amplitude against amplitude, until almost nothing is left, and a dark band appears where you might otherwise expect electrons to comfortably land. The stripes are not evidence of some contest between overcrowded electrons. They are the visible fingerprint of addition happening at the level of possibility itself, before any actual event occurs. It helps, maybe, to reach for an analogy from something more familiar, even though we will need to hold this analogy loosely, the way you might hold a delicate paper lantern, careful not to grip it so tightly that it crumples. Think of ripples spreading across the surface of a still pond after two pebbles are dropped in at slightly different spots. Where the peak of one ripple meets the peak of another, the water rises higher than either ripple alone would have made it rise, and where the peak of one ripple meets the trough of another, they cancel, and the water there stays nearly flat, undisturbed, as if neither pebble had been dropped at all. This is ordinary wave interference, the same phenomenon behind why certain seats in a concert hall sound louder or quieter than others, depending on how the sound waves bouncing off the walls happen to combine there. Waves in water or in air can add and cancel, just like probability amplitudes do. And this analogy is genuinely useful, historically useful too, since it was exactly this kind of behavior that convinced physicists in the early 19th century, long before anyone had heard of quantum mechanics, that light itself must be some kind of wave, because light produced exactly this pattern of bright and dark bands when passed through two narrow slits. But here, the analogy has to be handled with real care, because water ripples are made of actual water, a genuine physical substance rippling up and down in ordinary three-dimensional space, something you could scoop into a cup if you wanted to. The quantum wave function is not like that. It does not ripple through the space around us the way sound ripples through air. It exists, if that is even quite the right word, in a more abstract mathematical space, one that assigns amplitudes to possibilities rather than describing the motion of some physical fluid. And even more importantly, unlike water waves, which you can measure gently, dipping in a small sensor without much disturbing the wave itself, any attempt to directly examine the quantum wave function, to find out which slit the electron actually took, requires a genuine physical interaction, and that interaction is precisely what collapses all those delicate possibilities down into one single, definite outcome. Water ripples do not do anything like that when you dip a sensor into them, so we borrow the ripple analogy because it captures something true and useful about how amplitudes combine, while gently setting aside the parts of the analogy that would mislead us about what the wave function actually is, or where it actually lives. This is, honestly, one of the strangest features of the whole framework, and it is worth admitting plainly rather than smoothing it over. The wave function does something that no everyday analogy fully captures, because everyday objects simply do not behave this way. A wave in a pond is made of water molecules, each one occupying an actual location, moving up and down together. A crowd of people spreading out through two doors is made of individual people, each one taking one door or the other, definitely, whether or not anyone bothers to check. But the electron, described by its wave function, seems to genuinely explore both possibilities at once, in some mathematical sense that produces very real, measurable consequences, those stripes on the screen, without ever collapsing into a definite single path until something forces the issue. Physicists sometimes call this superposition, borrowing a word that suggests things layered one atop another, and that phrase does capture something of the flavor, even if no ordinary layering of physical objects behaves quite this way. The safest thing to say, the thing that keeps you closest to what the mathematics and the experiments actually show, is this. Before measurement, the system is described by a combination of possibilities whose amplitudes can add and cancel, and only measurement turns that combination into one concrete, actual outcome. Everything else, every metaphor about ripples or crowds or layered cards, is a ladder we climb partway up and then must be willing to set down, because the view from the top requires letting the analogy go and simply following where the mathematics and the patient decades of careful experiment behind it actually lead. Let this idea rest for a moment, because it leads us somewhere that people tend to misunderstand in a very particular way, and it is worth walking there slowly. In 1927, a young German physicist named Werner Heisenberg, working in Niels Bohr's Institute in Copenhagen, wrote down a relationship that would become one of the most famous and most frequently mangled ideas in all of physics. He found that there is a fundamental limit to how precisely you can simultaneously know a particle's position and its momentum, which is a technical way of saying its mass times its velocity, or loosely, how fast it's going and in what direction. The more precisely you pin down where something is, the less precisely you can know how it's moving. And the reverse holds too. Nail down the momentum with great precision, and the position blurs, spreads out, refuses to sit still in your description. Now, the first thing to say, gently but firmly, is what this is not. This is not a statement about clumsy instruments. It is not saying that our microscopes are too blunt, or our measuring devices too crude, or that some future engineer might build a cleverer gadget and get around the problem. That was actually a very natural first guess, and it's the one most people reach for instinctively, because in ordinary life, uncertainty usually does come from bad tools. If I ask you how fast a car is going and exactly where it is at this precise instant, and your radar gun is a little sluggish, or your stopwatch has some lag in it, you'll get a fuzzy answer, and a better instrument would sharpen that answer right up. Heisenberg's uncertainty is not that kind of fuzziness. It is not a limit on our knowledge that better engineering could someday dissolve. It is, as far as the theory and nearly a century of experiments have been able to tell us, a limit on how sharply position and momentum can even be said to exist together, for a quantum system, at the same time. The particle itself, in some sense, does not possess a perfectly definite position and a perfectly definite momentum simultaneously. It isn't that the values are there, hidden from us, waiting to be uncovered by a sufficiently gentle probe. The values themselves resist being simultaneously sharp. This is a strange enough claim that it deserves a slower unpacking, and a homely image might help, even though, as always, we'll need to let it go eventually. Imagine trying to determine both the exact pitch of a musical note and the exact instant it occurred. If a note rings out for a long, sustained duration, you can measure its pitch with wonderful precision, because pitch is really a statement about how many times a wave oscillates per second, and a long, sustained tone gives you plenty of oscillations to count and average and nail down. But you've lost any sense of a precise moment, because the note isn't really located at any one instant. It's smeared across the whole duration it was played. Now imagine the opposite, a single, sharp, percussive click, like a snap of the fingers. That click has a very definite moment in time. You could say almost exactly when it happened. But ask what pitch it was, and the question starts to fall apart, because a click that brief doesn't have enough time to establish a clean, well-defined oscillation. If you were to run a mathematical analysis on that click, you'd find it's actually made up of a huge spread of many different pitches, all overlapping, blurring together, precisely because it was so brief. This isn't a flaw in your ear, or a limitation of your hearing. It is a genuine feature of what sound waves are, and how time and frequency relate to each other mathematically. A wave that is sharply localized in time is necessarily spread out in frequency, and a wave that is sharply defined in frequency is necessarily spread out in time. You cannot have both pinned down at once, no matter how good your ears are. This trade-off between a wave's spread in one domain and its spread in another turns out to be a completely general mathematical fact, one that shows up whenever you're dealing with waves of any kind: sound waves, water waves, radio waves, and, as it turns out, the wave function we talked about a moment ago. And here is the deep connection Heisenberg and others uncovered. Momentum, in quantum mechanics, is tied to the wavelength of a particle's associated wave, in a relationship first proposed by the French physicist Louis de Broglie a few years earlier. A particle with a very definite sharp momentum corresponds to a wave with a very definite sharp wavelength, one long, clean, regular oscillation stretching out over a wide region of space. But a wave that stretches out over a wide region of space doesn't have a well-defined location. It's everywhere along that stretch, more or less equally. To pin the particle down to a narrow region of space, to give it a sharp, definite position, you have to combine many different wavelengths together, overlapping and interfering, so that they cancel out everywhere except in that one narrow region. But a combination of many different wavelengths means a combination of many different momenta. So sharpening the position, in this wave picture, necessarily blurs the momentum, and sharpening the momentum necessarily blurs the position. It's the very same mathematical trade-off as the musical note and the click, just translated into the language of matter waves instead of sound waves. What makes this genuinely different from an engineering problem is that this trade-off exists in the mathematics of waves themselves. Prior to any act of measurement, prior to any instrument touching the system at all, it's baked into what it means for something to be describable as a wave phenomenon. So when physicists say the electron doesn't have a simultaneously well-defined position and momentum, they're not being coy or mysterious for effect. They're describing something that follows directly from treating matter, at the smallest scales, as governed by wave mathematics, the same mathematics that gives you the interference stripes on the screen from a few sections ago. The uncertainty isn't a curtain drawn over a hidden, definite reality. As far as the theory describes it, and as far as generations of careful experiments have been able to probe, there simply isn't a hidden, definite pair of values sitting back there waiting to be revealed. It's worth pausing on how peculiar this is, because it runs against something almost every one of us assumes without ever examining it, the assumption that objects in the world always possess definite properties, whether or not anyone happens to be looking. A ball rolling across a table has a position and a velocity, full stop, even in the dark, even with your eyes closed, even if no one on Earth is paying it any attention. Quantum mechanics, at least as standardly understood, asks us to set that assumption aside, at least for certain pairs of properties, at the scale of electrons and photons and atoms. Position and momentum form what physicists call a pair of incompatible observables, meaning they cannot both be assigned sharp, simultaneous values, not because we lack the technique, but because the system itself, described this way, doesn't harbor both values at once with unlimited precision. And position and momentum are not the only such pair. There are other incompatible observables scattered throughout the quantum world, other properties that trade off against each other in the very same mathematical way, so that sharpening one necessarily blurs another. We'll meet a few of these before long, and each time, the lesson will echo this one. The blurriness isn't a failure of measurement. It's a structural feature of how nature, at this scale, seems to actually work, however unfamiliar and however quietly unsettling that might feel on first hearing it. Let's bring this abstract blurriness down to something you can almost picture, something that has been sitting quietly in front of you your entire life without asking for much attention. An ordinary atom, maybe a carbon atom, one of the countless billions making up the sheets or the mattress beneath you right now. For a long time, the picture people carried around in their heads, and the picture many of us were handed in school, was borrowed straight from astronomy. A dense little nucleus sits in the middle like a sun, and electrons circle it like planets, tracing neat, precise orbits, held in place by electrical attraction instead of gravity. It's a tidy image. It fits on a chalkboard in about 4 seconds. And it's wrong. Not wrong in some minor technical way, but wrong in a way that misses almost everything interesting about how atoms actually behave. The planetary picture came from a physicist named Ernest Rutherford, working in Manchester in 1911, who fired tiny charged particles at a thin sheet of gold foil and found that most sailed straight through, as though the foil were mostly empty space, while a small fraction bounced back sharply, as though they'd struck something small, dense and heavy. From that scattering pattern, Rutherford inferred the nuclear atom, a compact core surrounded by a great deal of emptiness. It was a real discovery and a startling one, but it left an immediate puzzle. If electrons really did orbit a nucleus the way planets orbit a sun, classical physics predicted they should spiral inward in a fraction of a second, radiating away their energy as they went, and every atom in the universe should have collapsed long before now. Obviously, that doesn't happen. The chair holding you up, the air moving in and out of your lungs, all of it depends on atoms being stable, stubbornly and reliably stable, for billions of years at a stretch. The fix came from a young Danish physicist named Niels Bohr, just 2 years after Rutherford's experiment, and it was a strange fix, a patch rather than a full explanation, though it pointed the way towards something deeper. Bohr proposed that electrons could only occupy certain specific orbits, certain allowed distances from the nucleus, and nowhere in between. An electron could jump from one allowed orbit to another, but it couldn't drift gradually inward the way the old physics demanded. It was as though someone had told you a marble on a ramp could only ever come to rest at certain fixed heights. never anywhere else along the slope, with the space between those heights simply forbidden to it. Strange, yes, but it worked remarkably well, at least for hydrogen, the simplest atom, with its single proton and single electron. Bohr's rule correctly predicted the exact colors of light that hydrogen atoms give off, colors that had been measured precisely for decades without anyone understanding where the numbers came from. Those colors are worth sitting with for a moment, because they were the clue that made the whole problem impossible to ignore in the first place. If you take hydrogen gas and excite it, say by running an electric current through it, the way a neon sign works, though with a different gas, it doesn't glow with a smooth, even rainbow, all colors blending into each other the way they do in ordinary sunlight passed through a prism. Instead, it glows with a small number of sharp, distinct lines, particular reds and blues and violets, and nothing at all in between them. Every element has its own signature set of lines, its own private fingerprint of color, and those fingerprints had been catalogued meticulously through the entire 19th century by scientists staring through spectroscopes without any theory to explain why the lines fell exactly where they did. It was one of those situations, familiar throughout the history of science, where a mountain of careful data sat waiting, patiently, for the idea that would finally make sense of it. Bohr's answer was that light comes from electrons jumping between his allowed orbits. Each orbit corresponds to a specific energy, and when an electron drops from a higher orbit to a lower one, the atom sheds the difference in energy as a single particle of light, a photon, with a color determined exactly by the size of that energy gap. Because only certain orbits are allowed, only certain gaps are possible, and so only certain colors ever appear. The sharp lines in the spectrum are a direct portrait of the atom's internal quantized structure, written out in light for anyone with a prism and the patience to look. It's a lovely idea, and it earned Bohr a great deal of well-deserved credit. But it was also, in the end, a stopgap. It borrowed the language of orbits, of paths and definite positions from the old physics, even while insisting that only some of those orbits were permitted, and it never explained why. It got the right answers for hydrogen through a kind of inspired guesswork, and it got the wrong answers, sometimes badly wrong, for almost every other atom on the periodic table. The deeper explanation came a little over a decade later, once physicists had the full mathematics of quantum mechanics in hand, the same wave-based mathematics behind the interference patterns and the uncertainty relations we've already spent time with. In that fuller picture, an electron bound to a nucleus isn't tracing any path at all, orbital or otherwise. It's better described by something physicists call an orbital, a word chosen to sound a little like orbit while meaning something quite different. An orbital is a kind of standing wave pattern, a cloud-like distribution describing where the electron is likely to be found if you were to measure its position, spread out around the nucleus in a particular shape. Some orbitals are simple spheres, thickest near the nucleus and fading gradually outward, like fog settling densest near the ground. Others have the shape of a pair of teardrops pressed together at their points, or four lobes arranged like the petals of a flower. None of them are paths an electron travels along the way a planet travels along its ellipse. They are, instead, the full and complete description of the electron's possible locations, all at once, the way a plucked guitar string vibrates as a whole shape, rather than a single point moving back and forth. Crucially, each of these orbital shapes corresponds to a specific, fixed amount of energy, and only certain shapes, certain energies, are allowed for a given atom, in a way that echoes Bohr's forbidden gaps, but rests on firmer ground. This quantization of energy is really the heart of what makes atoms atoms. It's why a given element always produces exactly the same spectral lines, whether you're looking at a gas cloud in a laboratory on Earth or light arriving from a star hundreds of light years away, light that left its source before you were born and carries, folded into its precise colors, the unmistakable signature of hydrogen or helium or iron, translated across that entire span of space and time. There's one more property worth introducing here, quietly, because it will matter enormously for understanding why matter holds itself together the way it does. Electrons carry something called spin, a name borrowed from the everyday world, though it's worth saying gently that this isn't a tiny sphere physically spinning on an axis, not in the way a top spins on a table. Spin behaves, mathematically, a little like rotation, and it comes with its own kind of directionality. But electrons don't have a size or a surface for anything to spin around in the ordinary sense. Every electron, everywhere in the universe, carries exactly the same fixed amount of this quantum property, differing only in which of two possible orientations it happens to have, orientations physicists label, for lack of more evocative words, up and down. This modest little property, so easy to state and so hard to picture, turns out to be the thread that leads directly to the exclusion principle, and to the reason why atoms stack together into the solid, textured, endlessly varied world of ordinary matter, rather than collapsing into a single, indistinguishable heap. Now, let's follow that thread of spin a little further, because it leads somewhere strange, somewhere that troubled Einstein for the rest of his working life, and somewhere that modern experiments have now tested with a thoroughness that would have astonished him. Imagine two electrons that come into being together, born from a single event, a single decaying particle, in such a way that their spins must be opposite, not because anyone measured them and decided this, but because some conservation law, some bookkeeping rule of the universe, requires that if you add their spins together, you get zero. This is a very ordinary kind of correlation, on its face. If you and a friend each take one glove from a pair, without looking, and travel to opposite ends of the world, then when you open your box and find a left glove, you instantly know your friend's box contains a right glove. Nothing mysterious there. The gloves were always left and right, from the moment they were packed, and separating them didn't create the correlation, it just hid two already existing facts from you. For decades, this is more or less how physicists assumed entangled particles worked too. Send two particles off in opposite directions, and each one carries with it some hidden, definite property, decided at the moment they separated, waiting to be revealed once someone finally measures it. Einstein, working with two younger colleagues, Boris Podolsky and Nathan Rosen, wrote a paper in 1935 laying out exactly this kind of argument, now known by their initials as the EPR paper. Their point wasn't really about entanglement itself. It was a challenge to quantum mechanics as a complete description of reality. If measuring one particle instantly tells you the state of another, far away, without any signal passing between them, then either something is traveling faster than light, which seemed absurd, or the particles had those properties all along, hidden variables that quantum mechanics simply fails to describe. Einstein preferred the second option. He wanted the world to be, underneath the uncertainty, orderly and definite, with particles carrying real properties whether or not anyone was looking. He called the alternative, the idea of instantaneous influence across any distance, spooky action at a distance, and he meant it as a criticism, a reason to think quantum theory was incomplete rather than final. For nearly 30 years, this stayed mostly a philosophical disagreement, a matter of taste almost, because nobody could see how to test it. The two pictures, hidden properties decided in advance, or something genuinely unsettled until measurement, seemed to predict exactly the same experimental outcomes. There was no obvious way to tell a stubbornly definite pair of gloves from a genuinely undecided quantum pair, since both would show you perfectly correlated results whenever you compared them. Then, in 1964, a physicist named John Stuart Bell, working at CERN, found a way to ask the universe directly which picture was true. Bell's insight was subtle, but, once you see it, oddly satisfying, like watching someone find the one loose thread in a tightly woven argument. He realized that if particles carry hidden, predetermined properties, then there are limits, mathematical limits, on how strongly correlated the results of certain measurements can be, no matter what those hidden properties happen to be, no matter how cleverly they're arranged. Picture it this way. You and your friend, still with your gloves, agree in advance that when your box arrives, you'll open it and check not just left versus right, but also, say, a strip of texture along one seam, checked at one of several possible angles you each choose independently after your boxes have already separated. If the gloves were fully determined from the start, fixed in every property, then no matter which angle each of you happens to choose, the pattern of agreement and disagreement across many repeated trials has to fall within a certain range. It can't exceed a specific ceiling. That ceiling is what we now call a Bell inequality, and any theory built on locally stored, predetermined properties, any theory in the spirit of Einstein's hidden variables, has to respect it. Quantum mechanics, when you work through the mathematics for entangled particles, predicts something different. It predicts that under the right conditions, the correlations can climb higher than that ceiling allows, not infinitely higher, not without any limit at all, but higher than any local hidden variable theory could ever produce. This was the crucial thing Bell had done. He'd turned a philosophical dispute, a question of taste about how to interpret an already agreed-upon theory, into a number you could actually go out and measure in a laboratory. And people did go and measure it, starting in the early 1970s, and continuing through a beautiful, painstaking series of experiments by physicists including John Clauser, Alain Aspect, and later Anton Zeilinger. Laboratories around the world built devices to create pairs of entangled particles, usually photons, send them off in opposite directions, sometimes many meters or even kilometers apart, and measure their properties along randomly chosen angles, choosing those angles as late as possible, sometimes even while the photons were already in flight, so that no signal, not even one moving at the speed of light, could pass between the two measuring stations in time to somehow coordinate the results. Alain Aspect's experiments in the early 1980s were especially important for closing that particular loophole, and decades later, in 2015, several groups performed what are called loophole-free Bell tests, experiments designed so carefully that essentially every alternative, mundane explanation for the results had been ruled out. Clauser, Aspect, and Zeilinger shared the Nobel Prize in Physics in 2022 for this body of work, for taking a thought experiment born of philosophical unease and turning it, patiently, over decades, into some of the most rigorously tested results in all of science. And every single time, in experiment after experiment, the correlations violated the Bell inequality. They came out higher than any theory of local, predetermined, hidden properties could explain, which means the comforting picture of the gloves, packed and decided in advance, simply doesn't describe what's happening with these particles. Something about their relationship really does resist being reduced to two separate objects, each quietly carrying its own private, definite instructions. Now, here's where it becomes very important to slow down and be precise, because this is exactly the point where popular explanations tend to run off the rails into something closer to mysticism than physics. It's tempting when you hear that measuring one particle seems tied to the state of another, however distant, to imagine some kind of instant message flashing between them, a whisper crossing the galaxy faster than light. But nothing of the sort happens, and this isn't a minor technicality. It's essential to how the whole picture holds together. If you're holding one particle from an entangled pair, and you measure it, you get a genuinely random result, heads or tails, up or down, with no way to control which outcome you get. Your friend, far away, holding the other particle, also gets a genuinely random result when they measure theirs. It's only when the two of you later compare notes, by ordinary means, a phone call, a message, something traveling no faster than light, that you discover your results were correlated in that stronger than classical way. Neither of you can use this to send information faster than light, because neither of you can control your own outcome, and neither of you learns anything about the other's result until the ordinary, light-speed limited comparison happens. The correlation is real, and it is strange, but no signal, no message, no usable information ever outraces light to make the trip. So what are we left with, if not hidden variables, and not faster than light signaling either? We're left with something quantum mechanics has been telling us patiently all along, that entangled particles, however far apart, are described by a single, shared mathematical description, a joint state that doesn't fully separate into independent stories for each particle on its own. It's less like two gloves in two boxes, and more like two pages that were always part of the same sentence, a sentence that only finishes being written once you read one page, and even then, the other page doesn't announce itself to anyone until you go and check. Now, if two particles that have never been in the same room can share a description that only settles into definite outcomes when someone looks, a natural question creeps in, and it's one that kept physicists awake, sometimes literally, for the better part of a century. What exactly counts as looking? What is a measurement, physically speaking? Where, in the chain of events between a particle doing whatever particles do and a scientist reading a number off a dial, does the fuzzy, spread-out possibility become a single, definite fact? This is called the measurement problem, and it sits at the center of quantum theory like an unlit room at the middle of an otherwise well-mapped house. Here's why it's such a stubborn puzzle. The equations of quantum mechanics, the ones that tell you how a wave of possibility evolves over time, are smooth and continuous and, in a very precise sense, gentle. Nothing sudden happens in them. A particle's wave function drifts and spreads and interferes with itself exactly the way a ripple on a pond does, predictably, continuously, with no jumps. But when you actually measure something, when you catch a photon on a detector or read a spin off an instrument, you don't get a smooth blend of possibilities. You get one answer. Click. It's this way and not that way. The smooth equation, left alone, never predicts that kind of abrupt, all-or-nothing outcome. Something else seems to happen at the moment of measurement, something the core equations don't describe, and physicists have spent a long time arguing about whether that something is a real physical event, a change in our knowledge, or a sign that we're misunderstanding the whole situation. Erwin Schrödinger, the same physicist whose equation describes that smooth, wave-like evolution, found this whole business deeply unsatisfying, and in 1935 he wrote a paper meant to needle his colleagues about it, particularly the emerging Copenhagen view associated with Niels Bohr and Werner Heisenberg, which treated the wave function as collapsing into a definite state the instant a measurement occurred, without saying much about what a measurement actually was, physically. Schrödinger wanted to show how strange that view became, if you didn't stop at the scale of atoms, but let it run all the way up to the scale of everyday objects. So he proposed a scenario, one he intended as a kind of reductio ad absurdum, a way of saying, follow this logic and see where it leads you. Picture a sealed steel chamber, opaque enough that nothing about its interior can be known from outside. Inside, place a cat, and alongside the cat, a small amount of a radioactive substance, so small that in the course of an hour, there's exactly a 50% chance one atom of it will decay. Rig the chamber with a detector that, if it registers a decay, triggers a hammer that shatters a vial of poison, killing the cat instantly and painlessly, at least in the telling. If no decay is registered, nothing happens, and the cat goes on doing whatever cats do in steel boxes, which is presumably napping. Now, radioactive decay is a genuinely quantum event. Nobody can predict exactly when a given unstable atom will decay, only the odds over a given stretch of time, the way you can't predict which grain of sand falls off a dune first, but you can predict roughly how the pile behaves. Before anyone opens the box and checks, standard quantum reasoning says that atom exists in a superposition, a combination of having decayed and not having decayed, both possibilities present at once in the mathematics, the way a coin spinning in the air isn't yet heads or tails, but a blend of both. Schrödinger's question, and it was a pointed one, was this: if the fate of the cat is chained directly to that atom, and if we take the collapse story literally, wouldn't the cat itself, before anyone opens the box, have to be described the same way? Not dead, not alive, but some blended, superposed combination of both, a genuine, physical 50-50 smear, stretched across an actual, furry, breathing animal, resolved only into one outcome or the other, the instant a curious physicist lifts the lid and looks inside. Schrödinger did not believe this was really happening. That was rather the point. He thought it was obviously absurd, that no one seriously believes a cat can be simultaneously alive and dead, half breathing and half still, in any way that matches how we understand cats, or breathing, or death. His thought experiment was a challenge, aimed squarely at the idea that quantum superposition simply scales up unaltered from atoms to animals, and that measurement is the only thing standing between blur and definiteness, with no account of why a cat should behave any differently from an atom just because it happens to be bigger and furrier and prone to sleeping in sunbeams. For a long time, this puzzle sat there mostly as a philosophical irritant, something physicists gestured toward uneasily in lecture halls without a satisfying resolution. But over the past several decades, a great deal of that irritation has been addressed, not entirely resolved in every philosophical sense, but substantially clarified through a body of work known as decoherence. And decoherence, despite its slightly clinical name, tells a rather intuitive story once you sit with it. The idea is this: a delicate superposition, one where two possibilities genuinely interfere with each other the way two ripples on a pond can reinforce or cancel, depends on those possibilities staying isolated from their surroundings, undisturbed, unentangled with anything else. This is achievable, with enormous care, for a single atom or photon in a laboratory, kept cold and shielded and nearly alone. But a cat is not alone. A cat is made of on the order of 1 trillion atoms, all jostling, radiating faint warmth, exchanging air molecules with the inside of the box, its heartbeat sending pressure waves outward, its very presence subtly influencing the electromagnetic field around it in 100 small, unavoidable ways. Every one of those interactions is, in effect, a tiny measurement, a leaking of information about the cat's state out into its environment. whether or not any conscious being ever peers through a window. The moment the mechanism linking that radioactive atom to the vial of poison operates, the states corresponding to decay and non-decay stop being cleanly isolated possibilities and become entangled with an enormous, sprawling number of environmental degrees of freedom, air molecules, stray photons, the metal of the box itself. The interference between the two possibilities, the very thing that makes superposition strange and wave-like in the first place, gets spread out and effectively erased, not because anyone looked, but because the information about which branch occurred has already leaked out into so many places at once that recombining it, undoing that spread, becomes as practically impossible as unscrambling an egg or unmixing cream from coffee. The two possibilities become what physicists sometimes call, effectively, classical alternatives, no longer able to interfere with one another, behaving for all practical purposes like ordinary, separate, mutually exclusive outcomes, the way a coin that has already landed and been covered by a hand is either heads or tails, not some blend of the two, even before anyone lifts the hand away. This is why cats and coffee cups and coins and every other object you can hold and drop and see with your own two eyes never seem to wander around in visible superpositions the way a single photon can. It isn't that some special rule switches on at a certain size or weight. It's that anything large enough to be made of trillions of particles is, essentially always, already thoroughly entangled with its surroundings before you ever get near it with an instrument. And that entanglement does the work that used to be mysteriously attributed to a conscious observer glancing through a window. What decoherence does not fully settle, though, and this is worth sitting with quietly rather than rushing past, is the deeper philosophical question of what a superposition actually is between the moment it's created and the moment it decoheres, and whether the universe truly settles on one single outcome, or whether, in some framework, all the possibilities remain real in some sense, just no longer able to talk to each other. That disagreement about what the mathematics is actually describing underneath the successful predictions is where the different interpretations of quantum mechanics begin to diverge from one another, each taking the same equations and telling a different story about what they mean. Let's follow one particular consequence of superposition a little further, because it turns out to be one of the more startling ones, and it has nothing to do with cats or coins at all. It has to do with something as small and ordinary sounding as a ball rolling toward a hill. Picture a marble rolling along a valley floor toward a low rise. If the marble doesn't have enough speed, enough energy, to climb over the top, it rolls part way up, slows, and rolls back down. That's the whole story, in the everyday world governed by classical physics. No amount of waiting changes the outcome. The marble either has enough energy to get over the hill, or it doesn't, and if it doesn't, it never will, not without some outside push. A quantum particle behaves differently, and the difference comes from the same wave nature that gave us those interference patterns and those spread-out probabilities we've been sitting with. A quantum particle approaching an energy barrier isn't a little marble at all. It's better pictured as something like a ripple of probability, a wave that, when it meets a barrier, doesn't simply reflect back the way water reflects off a seawall. A thin, faint trace of that wave actually leaks into the barrier itself, decaying as it goes, growing dimmer and dimmer the deeper it penetrates. And if the barrier is thin enough, that faint trace doesn't fully die out before it reaches the other side. It emerges, weakened but real, as a small but genuine probability that the particle has appeared beyond the barrier, on the far side of a wall it never had enough energy to climb over. Physicists call this quantum tunneling, and the name is apt, if a little misleading, because nothing actually drills or burrows through anything. The particle doesn't cross the barrier by force. It's simply, probabilistically, sometimes just there, on the other side, the way a value written faintly in pencil might, with enough patience, still be read through the page. This isn't some rare laboratory curiosity, dreamed up to make a point in a physics lecture. It's happening, right now, inside you and around you, on a scale so vast it's almost hard to hold in the mind. Deep inside the nucleus of certain unstable atoms, an alpha particle, a tight little bundle of 2 protons and 2 neutrons, sits trapped by the strong nuclear force, the way that marble sits in its valley, unable to climb out under its own power. And yet, unpredictably, after some span of time that can be measured but never precisely predicted for any single atom, that alpha particle tunnels free, and the atom decays, transforming into a lighter element and releasing a small burst of radiation in the process. This is radioactive decay, the same phenomenon behind the slow, steady ticking of a Geiger counter and the long, patient arithmetic of carbon dating. In 1928, a young physicist named George Gamow, working independently of similar ideas developed around the same time by Ronald Gurney and Edward Condon, showed that this quantum leaking through the nuclear barrier explained something that had puzzled physicists for years: why different radioactive elements decay at such wildly different rates, some in fractions of a second, others over billions of years, even though the physics governing them seemed, on the surface, so similar. And tunneling reaches even further outward, all the way to the stars, including the one currently, at this very hour, sitting quietly below the horizon while you rest. The sun generates its energy by fusing hydrogen nuclei together, but there's a puzzle buried in that simple sentence. 2 protons, both positively charged, repel each other fiercely, and by ordinary classical reckoning, the temperatures at the sun's core, blisteringly hot as they are, still aren't nearly enough to slam 2 protons together with sufficient force to overcome that repulsion and fuse. Arthur Eddington had wrestled with a version of this puzzle in the 1920s, insisting the sun must be powered by fusion even before anyone could fully explain how the numbers worked out. It was tunneling, worked out in the astrophysical context by Gamow, along with Fritz Houtermans and Robert Atkinson, around 1929, that resolved it. The protons don't need to climb all the way over that repulsive barrier. They only need to get close enough that their overlapping quantum waves give them a real, if small, probability of tunneling through it. Multiply that small probability by the almost unimaginable number of protons colliding every single second inside a star, and you get a steady, sustained furnace, burning for billions of years. Without tunneling, by the classical accounting alone, stars simply wouldn't shine, or they'd need to be so much hotter that the universe as we know it, with its slow, patient chemistry and its planets and its long stretches of geological time, would look nothing like it does. Tunneling shows up closer to home, too, inside the very device you might be listening to this on. The Scanning Tunneling Microscope, built in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's research laboratory in Zurich, uses exactly this effect to image individual atoms on a surface, moving an incredibly fine needle so close to a material that electrons tunnel across the gap between needle and surface, with the strength of that tunneling current revealing the terrain below, atom by atom, work that earned them the Nobel Prize a few years later. Tunnel diodes, developed by Leo Esaki in the 1950s, exploit the same phenomenon to switch signals with a speed that ordinary electronics can't match, and the flash memory chips that quietly hold your photographs and your saved documents work, in part, because engineers learned to coax electrons to tunnel through thin insulating barriers to store and erase tiny packets of charge. The world you touch every day is, in ways almost nobody stops to notice, threaded through with a quantum trick. there's a companion idea worth resting on here too, one that reframes what empty space even means. It's tempting to imagine a vacuum, a region with no particles in it at all, as simply nothing, a calm and featureless blank. But quantum field theory, the framework that treats particles like electrons and photons as ripples in fields that fill all of space, paints a stranger picture. Even in a perfect vacuum, those underlying fields are never perfectly, motionlessly still, because a field that was truly, exactly zero everywhere and unchanging would violate the same uncertainty that keeps a particle's position and momentum from both being pinned down at once. Instead, the fields jitter faintly, even with nothing around to jitter them, producing what physicists call vacuum fluctuations, sometimes described, loosely, as pairs of virtual particles flickering briefly into existence and vanishing again almost as quickly as they appeared. This isn't just a mathematical bookkeeping trick either. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged metal plates, placed extremely close together in a vacuum, ought to feel a faint attraction toward each other, because the plates would restrict which of those fluctuating field patterns could fit in the gap between them, compared to the unrestricted space outside. That force, tiny but measurable, has since been confirmed in careful laboratory experiments, direct evidence that empty space is quietly, restlessly alive with activity. Even the very stability of the atoms making up the quilt or pillow beneath you traces back to something in this same family of ideas, a restless, irreducible quantum jitter in every bound particle that keeps electrons from ever settling motionlessly into the nucleus they orbit. The reason matter holds its shape at all, rather than collapsing quietly in on itself. It's a strange thing to sit with, that the calm and steady world around you rests on a foundation that never sits fully still. And it raises, again, that quieter question we touched on a moment ago, about what's truly happening underneath all this flickering and leaking and settling, whether the universe is choosing one outcome from many or simply unfolding every possibility at once, unseen. That question about choosing versus unfolding has been sitting at the center of physics for about a century now, and it's worth being honest at this hour about something important. Nobody has resolved it. Not because physicists haven't tried, and not because the mathematics is unclear. The equations of quantum mechanics are some of the most successful, most precisely tested equations in the history of science. Where the disagreement lives is somewhere else entirely, in the question of what those equations are actually describing, underneath the numbers. And so, over the decades, a handful of different stories have grown up around the same shared mathematics, each one trying to answer that question in its own way, and each one, so far, impossible to rule out. The oldest of these stories is usually called the Copenhagen interpretation, named for the city where Niels Bohr ran his institute in the 1920s, where Werner Heisenberg worked out much of his early thinking on uncertainty. Copenhagen, in its most common telling, says something fairly practical, almost businesslike. It says that a quantum system, left alone, is genuinely described by a wave of possibilities, a spread of potential outcomes with no single one of them yet true. Measurement, in this view, is a real and distinct event, a moment when that spread collapses down into one actual, definite result. Before you look, the electron truly doesn't have a settled position. After you look, it does. The interpretation doesn't spend much time worrying about what a measurement really is, physically, or why looking should be different from anything else that happens in the universe. Bohr himself was somewhat famously resistant to being pinned down on the deeper metaphysics of it all. treating the theory more as a tool for predicting what experiments will show than as a window into some hidden underlying reality. For working physicists, calculating the behavior of atoms or the paths of electrons through a chip, this has always been enough. You don't need to settle what collapse really is, physically, to use the mathematics of collapse to get the right answer. But that very silence, on what a measurement actually is, on why the universe would treat human observation as special, has bothered plenty of people since, including physicists who admired Bohr deeply. And it led, in 1957, to a very different proposal from a young American graduate student named Hugh Everett, working at Princeton under John Wheeler. Everett's idea, now usually called the many worlds interpretation, takes a different way out. It suggests that collapse never actually happens at all. Instead, when a measurement occurs, every possible outcome is realized, each one branching off into its own separate, equally real version of the universe. In this view, when you measure an electron and find it on the left, there's another branch of reality, just as real, just as solid, where a version of you measured it and found it on the right. Nothing collapses. The wave never picks. It simply keeps spreading, and you, as an observer, simply end up as part of one branch among countlessly many, with no way of perceiving the others, in the same way you can't perceive a room you never walked into. Everett's paper attracted very little attention when it was first published. Wheeler himself found the idea difficult and encouraged some hedging of it. It's only in later decades, as physicists grappled harder with what measurement really means, that many worlds gathered a substantial following. It has one appealing feature, which is that it doesn't need a special rule for what counts as an observation. No odd boundary where ordinary quantum evolution suddenly stops and collapse takes over. It has one deeply strange feature too, which is that it asks you to accept an ever-branching, unobservable multiplicity of realities as the price of that tidiness. A third family of ideas takes yet another route, one that's older than Everett's, tracing back to Louis de Broglie's early work in the 1920s, and revived more fully by David Bohm in 1952. This is usually called pilot wave theory, or Bohmian mechanics. Here, there is no collapse, and there is no branching either. Instead, particles are given back something like the definiteness that classical physics always assumed they had. An electron, in this picture, really does have a specific position and a specific path at every moment, even when nobody is looking. But it's guided along that path by an accompanying wave spread out through space that shapes where the particle is likely to go, in something like the way a surfer's path is shaped by the swell of water beneath the board, even though the surfer is still a distinct, located thing riding on top of it. Pilot wave theory reproduces the same experimental predictions as the other interpretations, at least in the tested regimes, while restoring a picture where particles have real, continuous trajectories at all times. It has never attracted quite the following of Copenhagen or many worlds, partly because the mathematics becomes noticeably more awkward when you try to extend it to the more elaborate parts of quantum field theory, and partly, some have argued, simply because of the historical momentum Bohr's circle had already built up by the time it appeared. There are other proposals too, quieter ones, spontaneous collapse models that suggest wave functions might genuinely, physically collapse on their own, at random, without needing an observer at all, just extremely rarely, for small systems, and much more often for large ones, which is part of why chairs and clocks and sleeping bodies behave in such solid, definite ways, while single atoms stay so slippery. None of these ideas have been ruled out by experiment. None of them, so far, have been confirmed over the others either. What experiments have confirmed, again and again, with extraordinary precision, is the mathematics itself, the actual predictions about what outcomes will occur and how often. The interpretations sit one layer beneath that, in the realm of what the mathematics means, and that layer has stayed remarkably resistant to being settled by data, because the different stories tend to agree almost perfectly on what you'd observe in ordinary laboratory conditions, differing mainly in the picture they paint of what's happening when nobody's watching at all. There is one more open frontier worth mentioning gently before we let this rest, because it sits even further out past the interpretations, in territory where even the working mathematics hasn't been fully agreed upon yet. That's the question of quantum gravity. Quantum mechanics, in all its versions, describes the tiny, jittering, probabilistic world of particles and fields extraordinarily well. General relativity, Einstein's theory from 1915, describes gravity and the large-scale shape of space and time extraordinarily well too, treating that shape as something smooth and continuously curved. But nobody has yet found a single, fully working theory that describes both of these things at once, that says clearly what gravity looks like down at the tiny scales where quantum jitteriness ought to matter, inside a black hole, say, or in the first fraction of a second after the beginning of the universe. There are candidate approaches, string theory among them, loop quantum gravity as another, each attempting to weave the smoothness of curved spacetime together with the discreteness and uncertainty of the quantum world. None of them has yet produced a testable prediction that's been confirmed in the laboratory, and physicists working in these areas are generally quite careful, at least the honest ones, to describe them as promising mathematical frameworks rather than settled physics. So it's worth resting, for a moment, in this quieter kind of certainty. The measured, tested, endlessly confirmed part of quantum physics is solid ground you've been walking across this whole evening. The interpretations and the deeper unification with gravity are something else, open country still being mapped, where reasonable, careful people can look at exactly the same evidence and come away picturing the universe in quite different ways. And underneath all of that open country, underneath the interpretations and the unfinished search for a theory of quantum gravity, there is still the room you're lying in, right now, tonight, and it might be worth letting your attention settle there one last time before this ends. The mattress beneath you is made of atoms, and those atoms are mostly empty space, held apart and held together by the same electromagnetic forces we talked about earlier. The same rule that says electrons occupying the same orbital can't simply pass through each other, which is why the mattress feels solid under your weight instead of letting you sink through it like water. The particular firmness of it, the exact way it pushes back, traces down eventually to the Pauli exclusion principle, a rule Wolfgang Pauli worked out in 1925 while he was still in his 20s, sitting in Hamburg, trying to make sense of why electrons in an atom don't all collapse down into the lowest possible energy level and pile up on top of one another. They can't, it turns out, not because of some traffic law being enforced from outside, but because two electrons simply cannot share every single quantum property at once. That refusal to overlap completely is, in a very real sense, why anything in this room has a shape at all, why the walls hold their form, why your own body doesn't quietly seep into the sheets. The light in the room, if there's any left, whether it's the last gray wash of a street lamp through the curtain or the small red glow of some electronic display across the space, is made of photons doing what photons do, arriving as discrete packets even though they travel and spread the way waves do, refusing the whole time to be sorted neatly into one category or the other. If you'd shone a very dim beam of that same light through two narrow slits, one at a time, letting individual photons go one after another, they would still, patiently, over the course of many arrivals, build up the same banded interference pattern that light does when a whole flood of it goes through at once, as though each single photon were somehow checking both slits before deciding where to land. Nobody watching that experiment sees anything resembling a tiny object choosing a path. What they see is a pattern that only makes sense if the mathematics describing the photon's possibilities, the wave of probability itself, extends across both openings the entire time, and it's only that wave, not some hidden secret about the photon's actual location, that determines where the next flash on the detector screen is more or less likely to appear. And the air moving in and out of the room as you breathe, drifting past your face in the dark, is made of nitrogen and oxygen molecules, jostling in exactly the random, ceaseless way we described a few sections back. A randomness that adds up over the trillions upon trillions of collisions happening every second in a single breath, into something as steady and predictable as air pressure and temperature, into something you can plan a whole life around without ever giving the underlying chaos a second thought. That's the strange hinge this whole story keeps turning on, over and over, in one form after another, down at the smallest scale, the scale of a single electron's spin, or a single photon's path, or a single atom deciding when, exactly, within its unpredictable window, to release some particle of radiation. There is genuine, irreducible unpredictability, not a puzzle waiting for someone clever enough to solve it, but a basic feature of how nature seems to operate, confirmed now by nearly a century of experiments designed specifically to try to trip it up and expose some hidden mechanism underneath. And yet piled up together, scaled up by the almost incomprehensible numbers involved in anything you can actually see or touch or lie down on, that same unpredictability washes out into the steady, reliable, boringly solid world you've lived in your entire life. The world where dropped objects fall, where doors open the way you expect them to, where the sun rises on schedule and this room around you holds still. It's worth being honest, one more time, about what's actually settled here and what isn't, because that's really the difference this whole evening has been circling. The predictions are settled. Quantum electrodynamics, the theory describing how light and matter interact, has been checked against experiment to a precision matched by almost nothing else in the whole history of science. Agreement out to 10 or 11 decimal places in certain measurements, the kind of agreement that leaves essentially no room for the theory to simply be wrong about what it predicts. The technologies built on top of these predictions work reliably, whether or not the person using them has ever thought about quantum mechanics for a single moment. The transistor in the device charging somewhere near you tonight depends on quantum tunneling and on the specific, quantized way electrons are permitted to occupy energy levels inside a crystal of silicon. The laser reading a disk, if anyone still has one of those in the house, depends on stimulated emission, an idea Einstein worked out mathematically back in 1917, decades before anyone built a device to demonstrate it. Magnetic resonance imaging, sitting quietly in hospitals down the street from wherever you are, depends on nuclear spin, a purely quantum property with no equivalent at all in the ordinary world of things you can hold in your hand. None of that is speculative. None of it is waiting on some future experiment to confirm whether quantum mechanics actually works. It works. It has been working, reliably and repeatedly, for the better part of a century. What's unsettled, and it seems only fair to say this plainly, rather than let it blur into everything else, is the question of what any of it actually means, underneath the predictions, about the deeper nature of reality. Whether a particle genuinely has no definite position until it's measured, or whether it has one all along and we simply lack the tools to know it, whether the universe is quietly splitting into branches every time a measurement happens, whether there's some threshold of size or complexity where quantum weirdness gives way cleanly to ordinary classical behavior, or whether it's really weirdness all the way up, and we simply lose track of it in the noise, these are the parts still open, still argued over, in the way that has kept physicists occupied at conferences and in journals for 100 years running now, without any resolution in sight, and possibly none coming. It's worth resisting, gently, any account of quantum physics that reaches for grander claims than that, the kind that turn up sometimes in books or in conversation, claims that quantum mechanics proves that your thoughts shape reality, or that consciousness is what collapses the wave function, or that everything is secretly connected in some mystical sense simply because two particles once shared a common origin. Those ideas borrow the vocabulary of a real and rigorously tested science and stretch it toward conclusions the actual mathematics doesn't support. What the equations describe is stranger, honestly, and also more modest than that. Stranger, because the world genuinely doesn't behave the way intuition built from throwing rocks and rolling balls would lead you to expect. More modest, because none of it hands you control over outcomes just by wanting something differently. None of it says the universe cares what you're thinking about while you drift off tonight. So maybe that's the resting place for this whole long walk through the subject, appropriately enough, given the hour. A universe built out of rules that are, at bottom, probabilistic rather than certain, particles behaving like waves, and waves behaving like particles, depending entirely on how you go looking for them, entangled pairs correlated across any distance in a way that still can't be used to send so much as a single word faster than light allows. All of it worked out slowly, by particular people, in particular rooms, across 100 years of careful, argumentative, occasionally reluctant progress. It's a genuinely strange foundation, underneath a world that feels, from where you're lying, completely ordinary. And that gap, between the strangeness underneath and the steadiness on top, isn't a contradiction to be smoothed over, so much as a fact to leave sitting there quietly, the way a curtain doesn't need to be resolved in order to keep the room comfortably dark. The details can wait now, all of them, however they eventually settle. Rest well.